So we spent time reviewing oxidation numbers. We spent time reviewing oxidizing, reducing species and agents. What's being oxidized, what's being reduced, what does it mean? We talked about voltaic cells, also known as galvanic, and how we can identify what's being reduced, what's being oxidized based on cell potential. But let's go ahead and start talking about how this all relates to delta G. We've got your delta G, or your free energy of the reaction, and your cell potential. We're also going to use the Nernst equation. So if we have things under standard conditions, we can quickly calculate the overall delta G of the reaction. But if we're not under non-standard conditions, we have an equation known as the Nernst equation that helps us identify what would be the delta G value under non-standard conditions. So first, your cell potential and free energy. Remember, we are still talking about spontaneous reactions here, okay? We're still talking about galvanic, also known as voltaic cells. So a spontaneous reaction occurs when the driving force on the electrons, or the pull on the electrons, is positive. The driving force is what we call your electromotive force, or EMF. The difference in the potential, the driving force, which moves the electrons through that external circuit, is called your electromotive force, or EMF, or E-cell, which is measured in volts. I don't actually know what that little line there is on the screen. 1 second. That right there should just be E-cell. And so we've got this, okay? We've got your E-cell, which is known as your cell voltage. E-naught cell is your standard cell potential. And this is also equal to the standard cell potential of the reduced species plus the standard cell potential of the oxidized species. You will also sometimes see this written in the form of E-naught of your cell is equal to the E-naught reduction potential of your cathode minus E-naught reduction potential of your anode. So you will often see it written as cathode minus anode, looking at reduction potential specifically. The difference between these two equations here is in this equation, I have flipped the sign on the oxidized species. Meaning when I wrote the reaction the other direction, I flipped the sign like we do in Hess's law. In this version here, this is the more correct way to do it by an electrochemist, but in that one I have to remember it's cathode minus anode, and a lot of students have a hard time with that, so we're going to go ahead and flip it in our classroom, but again, you may see it written the other way. The superscript 0 in the E-naught stands for standard conditions. This means that every solute is at 1 molar concentration and every gas is at 1 atmosphere pressure. Again, we don't have to be at those conditions, but if we're specifying with that not symbol, that's what it means. We can measure this driving force, the EMF, by measuring the cell potential of the voltaic and or galvanic cell. The cell potential, so E-naught is my cell potential. Move that up to a higher font. I apologize, I hit the wrong button. E-naught is the difference in the potential energy between the anode and the cathode in a voltaic cell. So the potential energy difference is your cell potential, and that's what's going to allow those electrons to transfer. Again, in a voltaic cell, we also refer to these as galvanic cells. The redox reaction is spontaneous. Because it is a spontaneous reaction, delta G is less than 0. The cell potential will be greater than 0. And the equilibrium constant K will be greater than 1. So E-naught of my cell versus delta G-naught versus K, plus, minus, and greater than 1. And that is for voltaic cells. We're going to find something different when we start talking about electrolytic cells in a different module. How does current and voltage come into play? So 1 amp is 1 coulomb per second, and 1 volt is 1 joule per coulomb. Current is defined as the number of electrons that flow through the system per second. How many electrons are flowing per second? The unit here is an ampere. So ampere, or we call it amp for short. Again, 1 amp is 1 coulomb per second. That is current, the current of the system. 1 amp, 1 coulomb of charge flowing each second. 1 amp is equal to 6.242 times 10 to the negative 18th electrons per second. The surface area of an electron dictates the number of electrons that can flow. What do I mean by that? We've talked about developing these up. We've talked about putting these in beakers and separating out your system and having a piece of metal in there. That piece of metal that has the electrons being transferred is your electrode. The surface area of that piece of metal, whatever it may be, is what dictates how many electrons can actually flow. So if I've got a beaker and I've got an electrode in here, and this much of my electrode is covered, that is the surface area of my electrode. All sides that are exposed to solution is the surface area of my electrode. That surface area dictates how many electrons can flow. Because again, the electrons are coming off of that the electrons are coming onto and off of that electrode into solution. The potential energy difference between the reactants and 1 volt of force, 1 volt is 1 joule per coulomb of charge, is the potential difference, which is your potential or your volt. Again, 1 volt, 1 joule per coulomb. Your electromotive force, or EMF, is the amount of force pushing the electrons through the wire. It's the voltage that you need to drive the electrons through that external circuit. So again, electromotive force, EMF. How does delta G and K come into this though? The maximum cell potential is directly related to the free energy, delta G, difference between the reactants and products in that electrochemical reaction. But we can actually experiment to determine delta G and K. We know here, we see the correlations between them. Delta G is equal to negative NF E naught of the cell. What I've got written here is delta G naught is equal to negative NF E naught of cell. This means the standard cell potential is directly comparative to the standard free energy of the system. If I'm not under standard conditions, I can also calculate this at any potential. So even if I'm not under standard conditions, I can still use this. And again, down here, it's got everything defined. E naught of your cell is your standard potential. If I just write E of my cell, that's just my cell potential under non-standard conditions. N is the number of moles of electrons transferred, and F is what we call Faraday's constant. It's just a constant you're going to have to memorize, 96,485 coulombs per mole of electron. We can also see a correlation between delta G and K. Delta G naught is equal to negative RT ln of K. And then the correlation between cell potential and K, E naught of my cell, so my standard cell potential is equal to 0.0592 volts divided by N, number of electrons transferred, times the log of K. We also have the Nernst equation, because what if we are not under standard conditions? All of these equations, except this one, are for perfect standard conditions, meaning 1 molar concentration, 1 atmosphere pressure. But if I'm not under standard conditions, I can use the delta G equals negative NFE of the cell, but it's not under standard conditions. I need to figure out, how do I deal with that when I'm not under standard conditions, meaning not standard concentrations, not standard pressures. That's where the Nernst equation comes into play. The Nernst equation is used to determine the cell potential under non-standard conditions. The Nernst equation is listed as E, your cell potential, is equal to E naught, your standard cell potential, minus 0.0592 divided by N, number of moles of electrons transferred, times log of Q. where E is your cell potential under non-standard conditions. E naught is the cell potential under standard conditions. And I want to emphasize, these are the values calculated from the data in the tables. And by tables, I mean your standard reduction potential tables. N is the number of moles of electrons transferred. And Q is your reaction quotient. Which again we find by taking the concentration of your products raised to their respective coefficients divided by the concentration of reactants raised to their respective coefficients, and not including solids or liquids, only gases and aqueous phase, because solids and liquids are considered to be relatively constant in their concentration. But because of this, you must have a balanced equation, or this will not work. Okay? So, BCA charts are helpful in determining the changes in concentration over time. We can definitely see that. And then batteries, remember, voltaic cells, galvanic cells, same thing, are batteries. They will run until your equilibrium is reached. So once you reach equilibrium, Q is equal to K. Delta G is equal to 0. When Q equals K, you've reached equilibrium. Delta G is now equal to 0. The battery died. It's done. Your electromotive force, or E of your cell, is equal to 0. There's no more driving force. And again, solids do not affect the position. Their concentrations are not changing. So when you see like a solid copper electrode or a solid zinc electrode, it's not changing your Nernst equation. It does not go into Q. Let's do some examples. Describe the cell based on the following half reactions at 25 degrees C by calculating the cell potential, writing the balanced equation, and sketching the cell. We've got VO2 plus 2H plus an electron, give me VO2 plus H2O. The reduction potential here is 0.99 volts. And then we've got zinc 2 plus 2 electrons giving me zinc, and the reduction potential here is 0.76 volts. It tells me that the VO subscript 2 plus 1 charge has a 2 molar concentration. The H plus has a 0.5 molar concentration. The VO charge of 2 plus has 1 times 10 to the negative 2 molar concentration, and the zinc 2 plus has 1 times 10 to the negative 1 molar concentration. So, let's think about what's going on here. I've got this species versus this species. I'm going to look at the cell potentials and see which one's going to be oxidized and which one's going to be reduced. Remember the values here. They're both giving me reduction potentials here, okay? The reduction means gain. Oxidation means loss. The one that wants to be reduced, the one that wants to gain the electrons, is willing to pay the most in energy. 0.99 is a lot greater than 0.75, so this is the species that will be reduced. This is the species that will be oxidized. So this is going to be at my reduced is my cathode. Oxidized is at my anode. I'm going to go ahead and draw the diagram over here. If I could draw a straight line. Draw my salt bridge in. Now, at my anode, and I know my anode is always on this side, oxidation, and that's my negative terminal on a galvanic cell, cathode, reduction, and positive terminal. I have zinc and zinc 2 plus at my anode, so I'm going to go ahead and draw my zinc electrode and put my zinc 2 plus in solution. At my anode, I've got that zinc, this reaction happening. Now at my cathode, I've got all kinds of stuff in solution, right? I've got the VO2 plus, the H plus, the VO2 plus, and water. It's all dissolved in water. But I don't have a metal here. I don't have a solid phase here. So I'm going to have to put a solid phase in. I'm going to go ahead and use platinum. I'm then going to connect my zinc to my platinum. And that is completing my circuit. And I can measure that with a voltmeter if I want to. If I want to measure the voltage here. I've got the VO2 plus going to the platinum, forming VO2 plus. When I say that, I mean the VO subscript 2, positive 1 charge, giving me the VO positive 2 plus charge. So I've got it drawn. Let's go ahead and write my shorthand. I know my shorthand goes anode to cathode. So at my anode, I've got zinc, solid, phase separation, zinc 2 plus, aqueous. Now, my zinc is not at 1 molar concentration, so I'm going to write the concentration in here. 1.0 times 10 negative 1 is the same as 0.10 molar. You can write it either way, I don't care. I like not doing scientific notation if I don't have to. Salt bridge. My VO subscript 2 plus aqueous is a 2 molar concentration, comma, VO plus 2 charge, aqueous phase as well, 0.010 molar concentration, phase boundary, and my platinum electrode. So now I've got my shorthand. So I have completed sketching this out. I have written the shorthand, which I wasn't asked for, but I like to have shorthand in there because it makes my brain see it better. I want to write the balanced equation. And then I'm going to go ahead and calculate the cell potential of this as well. So let's go ahead and write the balanced equation. We know that the zinc is being oxidized. So I've got zinc, solid, going to zinc 2 plus 2 electrons. And the cell potential for this, I flipped this equation around, so now I'm going to flip this the sign on this. I'm going to make it positive. It's going to be 0.76 volts. The other reaction, I have VO subscript 2 plus 1 charge plus 2 H pluses plus an electron, giving me VO plus 2 charge plus water. Water is a liquid. Ions are going to be aqueous phase. I did not flip the reaction around, so my cell potential will stay the same at 0.99 volts. But this reaction is not going to be balanced when I add them up, right? I have to balance this out because I have to cancel out those electrons. So I'm going to multiply this through by 2. It gives me a 4 there. 2, 2, 2. Now, I didn't heavily emphasize this in the last video because I just didn't think about it. But no, when I multiply this reaction through by 2, I do not change the cell potential. I'm leaving the cell potential the same because it's the potential of that system. It's not based on the fact that I'm doubling the number of moles of the system. It's the potential energy of the reaction, okay? Do not change your cell potential. Leave the cell potential the same. Go ahead and add these up. Make sure your electrons should cancel at this point and add up everything else. Zinc solid plus 2 VO2 plus 1 charge, aqueous, 4 H plus, aqueous, gives me Zn2 plus, aqueous, VO plus 2 charge, aqueous, 2 moles of water, liquid, and the standard cell potential here is 0.76 plus 0.99, so 1.75 volts. But that is not the cell potential of this system because I'm not under standard conditions. So let's go ahead and figure out what that would be. I'm going to use the Nernst equation. my cell potential is equal to my standard cell potential minus 0.0592. What is that 0.592? The 0.592 is wrapping in some constants. It's wrapping in your gas constant, Faraday's constant. It's overall just taking care of some in the temperature. So gas constant, Faraday's constant, and the temperature of your system. It's assuming a 25-degree system. If you're not at 25 degrees C, we can't actually use 0.0592. It's it's wrapping constants together to get that value. Okay, so it's just simplifying it for you guys. Divided by the number of moles of electrons transferred times the log of Q. Well, I just figured out my standard cell potential was 1.75 volts, 0.0592. I know that 2 moles of electrons were transferred because I've got 2 electrons here, 2 here, times the log of Q. I want my concentration of my products over the concentration of reactants. This is why I like the balanced equation, because it helps me identify what's where. I know my zinc is 0.10 molar. The VO plus 2 is 0.010 molar. The VO subscript 2 plus 1 charge is 2 molar. And my H plus is 0.5 molar. So I know this is going to be, let me just, so we can actually write this out. I apologize. I know this is getting kind of messy, you guys, and I'm sorry. But so many things I want to teach you guys. Okay, so Q, I'm going to go ahead and erase that Q and put in there what we know. The log, concentration of zinc, 2 plus, times the concentration of VO, 2 plus, quantity squared. I definitely forgot to put the 2 there, so please fix your notes if you were just copying me directly. There should definitely be a 2 there. Times VO subscript 2 positive 1 charge squared times H plus to the 4th. Go ahead and put all those values in. So zinc 1.0 times 10 to the negative 1 molar is the same as 0.1 molar. I'm going to drop the units here because I'm going to take the log in a second anyway. The VO plus 2 charge is 1.0 times 10 to the negative 2 molar. 0.010 molar is the same. The VO subscript 2 positive 1 charge is a 2 molar solution. Okay, I'm going to put the squares in a sec. Let me get these concentrations in, and then 0.50 molar. Okay, this is squared, this is squared, this is to the 4th. Calculate all that through, and I get 1.64 volts. So my standard cell potential of this reaction, if everything was at perfect conditions, meaning everything was all at 1 molar, would be 1.75. What I find, though, is it's actually got a cell potential of 1.64 for this system. Let's work some more examples. Suppose an electrochemical cell was formed by connecting an H plus 1 molar H2 1 atmosphere half cell with zinc 2 plus 1 molar zinc half cell. Write the overall cell reaction to determine the cell potential. Okay, so for in this case, I've got H plus and H2. What I need to recognize is that is representing my standard hydrogen electrode. For ease, I'm going to go ahead and draw my line diagram to identify really quickly what's going to be where. I need to look these up, and I need to go get a table of standard reduction potentials, and I'm going to find that my H plus H2 is at 0 volts, and my zinc 2 plus zinc is at negative 0.76 volts, okay? Again, I do not know those values by heart. Well, I know the hydrogen by heart, but you're going to have to look those up. So you're going to have to recognize you have to go look those up. This is my electron flow. So this is my anode, where oxidation occurs, negative charge, cathode, reduction, positive charge. The difference between these two is 0.76 volts. So I know that my cell potential, I know overall I've got zinc here. Zinc solid is going to oxidize to form zinc 2 plus and 2 electrons. And that would be a positive 0.76 volts, because when I look up the cell potential, it's negative because I'm doing a reduction. And hydrogen is going to show 2 H plus ions gaining 2 electrons to form H2 gas, where the cell potential is 0. I want the overall cell reaction and the cell potential. So the overall reaction here is zinc solid plus 2 H plus, 2 moles of H plus, react to give me 1 zinc 2 plus and H2 gas. The overall cell potential here is positive 0.76 volts. Now, I know I didn't ask for it, but what if I wanted to write the shorthand here? I'm going to write my anode, zinc solid. The nice thing here is that my solid is on the solid that's on the reactant side, if there is a solid present, is the same solid you're going to write on that side of the reaction, okay, or on that side of the shorthand. Zinc solid, phase diagram, zinc 2 plus, aqueous. I then need to write the concentration here, and it is 1 molar. Salt bridge for phase to separate out the 2 half cells. Now on the other side, I've got H plus aqueous. That's 1 molar. I have to put a phase diagram in between the aqueous and the gas because they're different phases. H2 gas, 1 atmosphere. And then I have to have some kind of solid piece here, so I'm going to use platinum, because platinum is inert, to be able to generate the hydrogen gas off of. Because the concentrations here are 1 molar and 1 atmosphere, I'm under standard conditions, so what I find from that standard reduction potential is going to be the actual potential of the system. What if I wasn't under standard conditions, though? What would be the cell potential be for the cell above if the concentration of H plus was 1 molar and the pressure of H2 gas was 1 atmosphere, but the concentration of zinc 2 plus was 0.0100 molar? How do I find it then? Well, I'd have to do what I already did. I'd have to find the overall reaction and the overall standard cell potential, but luckily we just did that. So zinc solid plus 2H plus aqueous. I know this is 1 molar here. Gives me H2 gas, 1 atmosphere, plus zinc 2 plus, 0.0100 molar. And I know that the standard cell potential here is 0.76 volts. But now I'm going to use Le Chatelier's principle. Not Le Chatelier's, that's coming. I apologize. I'm going to use the Nernst equation. E equals E naught minus 0.0592 over N times the log of Q. Standard cell potential, 0.76 volts, minus 0.0592 over N. I've got 2 moles of electrons transferred, right? Zinc loses 2 electrons. Each hydrogen picks up 1 to form H2 gas and zinc 2 plus, so 2 electrons transferred, times the log of Q, products over reactants. I have 1 atmosphere, and you can mix pressures and concentrations here in the Q expression. So 1 atmosphere of H2 gas, 0.01 molar of the zinc 2 plus, my products, divided by 1 molar squared for H2 for the H plus concentration. Overall, this gives me 0.82 volts. Now, what I find here is that my calculated cell potential is greater. So my cell potential for this system is greater than my standard cell potential. 0.82 volts versus 0.76 volts. And I want you to think about why. Why am I seeing a higher cell potential here? And the truth of the answer is, I already gave it to you by accident, it's Le Chatelier's principle. He's back. Well, he never left. If I look at the concentrations here, 1 molar versus 1 atmosphere, no difference there, but 0.01 molar. The concentration of my product is a lot weaker, or not weaker, that's not the right word, a lot more dilute, a lot smaller than the concentration of my reactant. So by Le Chatelier's principle, to reach an equilibrium, right, this is a battery, it needs to run out, right? To reach equilibrium, I need the reaction to go in the forward direction. This is a good battery. It's going to have, the cell potential here is a little bit greater because I've got even less concentration over here, so I can actually pull a little more juice out of this battery. For the rest of this module, I'm just going to continue working in multiple examples. So if you feel comfortable with this, don't worry about continuing to watch. But I'm just going to work some more examples for you guys, because what I find is the more examples you work, the easier this stuff becomes. So what is the cell potential of a galvanic cell constructed from magnesium, magnesium 2+, and aluminum, aluminum 3+? Note here, it is not showing me concentration, which means we assume 1 molar, or standard conditions. So I'm going to look up the two reactions in a table, and I find aluminum 3+, aqueous, plus 3 electrons, giving me aluminum solid. And this has a standard cell potential equal to negative 1.66 volts. And then I have magnesium 2+, aqueous, gaining 2 electrons, giving magnesium solid. And the cell potential here is negative 2.37 volts. So, which one wants to be reduced more? Which one wants to be oxidized more? Who wants the electrons the most? Students often get confused about that. They often mix up which one wants it. So the way I kind of think about it is I think about it like a payment system. Who's willing to pay the most? I've got a negative 1.66 or a negative 2.37. The more negative the number, the stronger it will be at oxidizing. The more positive the number, the stronger it will be at being reduced. So they're both negative. And that's, I think, one thing that throws students off is they're both negative. But this one is less negative or more positive. So the aluminum is the species that wants the electrons most. Aluminum 3+, specifically, aluminum ion, wants the electrons more. So this will be reduced. While magnesium will be oxidized. So you have to compare those numbers. And it can throw students off because they're going to see a really big number and they're going to say, okay, 2.37 is bigger. It is, but it's more negative. You're looking for the more positive number. Think about it like on a, or if you get confused, think about it on the number scale again, okay? Because I can get confused sometimes too. The numbers kind of get in my head and I forget about what I'm doing. If I look at the number scale, negative 2.37 volts for magnesium 2+, versus negative 1.66 volts, aluminum 3+. It's always going to be your anode, where oxidation occurs, and your cathode, where reduction occurs, okay? Then I'm just going to write out the valence reaction. So I know that the aluminum is going to gain those electrons. So the aluminum is written correctly. The magnesium's reaction is going to be flipped around. So I'm going to have magnesium solid reacting with aluminum 3+, aqueous, to give me magnesium 2+, aqueous, plus aluminum solid. But I have to pay attention to electrons here. 3 and 2 do not balance. This whole system is going to have to be multiplied by 2. This is going to have to be multiplied by 3. Remember, we leave the cell potentials alone. They do not change. The cell potentials, it's your potential energy. They are not reliant about the number of moles in the reaction. So that's going to give me 2 aluminums, or 2 aluminum ion, 2 aluminum solid, 3 magnesium solid, 3 magnesium ion. Now it is balanced out, and my cell potential here is going to be negative 1.66 volts plus 2.37 volts. My overall cell potential for this reaction will be 0.71 volts, or the difference between these two numbers. What is the cell potential of the following reaction? I've got MnO4 minus plus H plus ClO3 minus, giving me ClO4 minus plus Mn2 plus H2O. Well, that's kind of confusing, right? I gotta kind of try to figure out how the heck to divide this reaction out. What is going on here? Well, there's a lot going on here. So what I have to do is I have to go back to that reduction table and figure out what reactions are actually involved in this overall reaction. When I go back to the table, I find MnO4 minus plus 8H plus 5 electrons is going to give me Mn2 plus 4H2O. And the standard cell potential for this is 1.51 volts. I also I found the MnO4 plus, and it had the Mn2 plus, and this was the reaction I could find. I'm now also going to look for something with ClO3 minus and ClO4 minus. I find one with ClO4 minus reacting with 2 moles of H plus and gaining 2 electrons to form ClO3 minus and water. And the cell potential here is positive 1.19 volts. Again, in case I get confused, I can always do my number line. And I can say, okay, 1.19 is definitely smaller than 1.51 volts. So the ClO4 minus, ClO3 minus versus the MnO4 minus, Mn2 plus. This will be my anode. It's going to be oxidized. Negative because I've got a galvanic or voltaic cell. This will be my cathode. It's going to be reduced at the positive terminal because it is, because it is a voltaic cell. So I know that this is a system that's going to be flipped. Now, I'm going to go ahead and move my cell potentials over a little bit just so I don't write among them. But before I add these together, I need to balance this reaction. I've got 5 versus 2. Okay, I'm going to flip this reaction around, and I'm going to flip the sign around. So I need you guys to write that out, but I'm just going to be lazy on this and flip things on you. So flip your equation around. When I do that, I also put a negative sign in front of here. Now I'm going to add these equations up to get my overall equation, but I have to balance my electrons. I've got 5 electrons here and 2 electrons here. They do not balance out. To balance them, I'm going to multiply this top reaction by 2 and this bottom reaction by 5. If I do that, that will give me 10 electrons on the top, 10 electrons on the bottom, or 10 electrons on the reactant side, 10 electrons on the product side, and they will therefore cancel out. So 2 MnO4 minus, aqueous. Remember, ions are always aqueous phase. Plus 8 times 2 is 16. 16H plus, aqueous. Plus 5 ClO3 minus. Plus 5 water. And I'm probably going to have to balance this a couple times. And I'll show you why in a sec. Plus 5 water is going to give me 2 Mn2 plus, aqueous. Plus 8 H2O liquid. I'm definitely going to run out of room. Plus 5 ClO4 minus plus 10 H plus. Now I do have to cancel out the extra waters and hydroniums or H plus on each side. 16 versus 10. That's going to cancel out my 10 and give me 6H plus here. So I'm going to erase the 16 here and write 6 H plus, and I'm going to erase the 10 here. I also have 5 waters versus 8 waters. It's going to cancel out the 5 and give me a 3 here. So the 5 here, and 3 H2O liquid here. That is aqueous phase. So you do have to look and make sure that you're canceling those out as well, okay? Then the overall cell potential is the difference between these. 1.51 minus 1.19. The difference here, 0.32 volts. Cell potential, 0.32 volts. And you have now solved another one. Describe the galvanic cell based on the following half reactions under standard conditions by calculating its cell potential, writing a balanced equation, and sketching the cell. Okay, so it gives me the reduction reactions, which are the standard reduction potential, and the reactions as written, which is nice. I don't have to think about it. I'm just looking them up, right? I do have to figure out which one is going to be oxidizing and which one's going to be reduced. Now, I can either just remember the more positive the number, the more it's willing to pay for that electron, the more it wants to be reduced, or I can do the number line. If I do the number line, 0.77 volts versus 0.80 volts. It's Fe2 plus to Fe3 plus versus Ag2 or Ag plus to Ag. I can see that the silver is going to be reduced and the iron plus 2 to iron plus 3 system is going to be oxidized because the silver is a little more positive in its cell potential. So let's see. Calculate the cell potential, write a balanced reaction. Okay. The silver is, when silver is reduced, it needs to gain 1 electron. That means that the iron has to give up 1 electron. Conveniently, that's the reaction I'm seeing. This reaction is going to be flipped around though. I'm going to have Ag plus the electron, giving me Ag. My cell potential will stay the same. 0.80 volts. Excuse me, this will be added to Fe2 plus, going to Fe3 plus an electron, and the cell potential is flipped around, so I find negative 0.77 volts. Again, this is solid. Ions are aqueous phase. So when I want to add up the overall reaction, I can add from here. I'm showing just, yes, my electrons are canceling. We're good to go. I get Ag plus, aqueous, plus Fe2 plus, aqueous, giving me Fe3 plus, aqueous, plus silver solid. Excuse me. And the overall cell potential for this reaction, or I could even, instead of writing cell, I could write E naught of reaction, is 0.03 volts. Remember your sig fig rules? Students really like to forget that rule. When you're adding and subtracting, you're keeping the same number of decimal places. So 0.80 and 0.77 each have 2 sig figs, but because I'm adding these two numbers together, I have to keep to the second decimal place. So my final answer, overall cell potential, is 0.03. Again, this part here, if you can do without writing it out, unless specified. If it is specified, you will have to show it, but what's written here in pink is your overall reaction. Now, it tells me I've calculated the cell potential. That's at 0.03 volts. I've written the balanced equation. It says sketch the cell. So let's go ahead and sketch your cell. I'm actually going to shrink down the equation a little bit just for space. So I'm going to have my 2 beakers connected by a salt bridge. I've got to have two things that are solid here, and they are connected as well. So my salt bridge, my circuit with my volt. Now, my reduction, so remember my solution, Anode, always on the left. Anode is where oxidation occurs. And this is the negative terminal. Cathode, always on the right. This is reduction occurs. Always positive. At my cathode, being reduced is my silver. So this is going to be a silver electrode with silver ions in solution. At my anode is where I've got iron being oxidized. Oxidation is loss, so it's losing electrons. So I've got iron 2 plus going to the surface and losing an electron coming off as iron 3 plus. In order to do that, it's got to have somewhere for the electron to come from, an electron to go. In this case, the electron's going, and we're going to use platinum. So the two reactions here, this is showing the iron 2 plus, giving me Fe3 plus an electron. Aqueous phase here and here. This is showing silver, gaining the electron, giving me silver solid here. And again, if I want to write the shorthand, last thing that I could, at least at the moment, think to ask you is a shorthand notation. I'm going to write your anode to your cathode. So I'm going to have to specify that platinum solid. I've got Fe, that's definitely not enough. Fe2 plus aqueous, Fe3 plus aqueous. If they were not 1 molar, if I was told concentrations and they were not 1 molar, I would specify them here. I would write a parenthesis and then write the concentration here. Because it's not specified, it's assumed to be 1 molar. Salt bridge separates out the anode to cathode, anode to cathode. Let's see, I've got silver ions. Those are aqueous, and then a phase separation to my silver electrode. So that is my shorthand, anode to cathode, because electrons always travel anode to cathode. And our last example for this unit. Using standard reduction values, calculate delta G for the reaction, determine if it's a spontaneous reaction. I've got copper 2 plus reacting with iron solid to give me copper solid and iron 2 plus. So, what's going on here? Well, it's clearly telling me which one's reacting with what, right? I've got copper 2 plus going to copper solid. In order for that to happen, copper 2 plus aqueous plus 2 electrons gives me copper solid. I look up that cell potential online, and written as a reduction, the cell potential is 0.34 volts. I've also got iron solid giving me iron 2 plus. If I look up the reduction reaction for iron 2 plus, that is definitely not a 2. Iron 2 plus aqueous plus 2 electrons giving me iron solid. The cell potential here is positive 0.45 volts. Or I apologize, that is a negative value. Getting ahead of myself. Negative 0.45 volts. So this one, going to be reduced. This is going to be oxidized, which is what we see in the reaction as well. So everything's matching up to what we see in the reaction. Overall, my cell potential here, E naught of my cell, is that 0.34 volts plus 0.45 volts. Because this equation's been flipped around, I flipped the sign on this, giving me a cell potential of 0.79 volts for this reaction. But I want delta G. I have to think back to that delta G value. Delta G naught is equal to negative NF E naught, negative number of moles of electrons transferred. I've got copper 2 plus being reduced to copper solid. I've got iron solid being oxidized to iron 2 plus. That means overall, 2 moles of electrons have been transferred. Faraday's constant is 96,485 coulombs per mole of electron transferred. And my voltage here is 0.79 volts. Remember what a volt is, though. We saw that. Let me scroll back for you guys for review. I don't remember exactly where that was. I apologize. Here. 1 volt is 1 joule a second. So this is how I'm going to get to the right units here. Scroll back down. Here we go. And instead of volt here, I'm going to write joule coulomb. That's going to help me identify how my units are canceling. Moles of electrons cancel, coulombs cancel, I'm left with joules. I calculate this out, delta G naught equal to negative 152,446 joules. I have to think about my sig figs here. This is exact. This is 5 sig figs. This is 2 sig figs. So I need 2 sig figs in my final answer. Negative 150,000 joules, or more commonly written as kilojoules, negative 150 kilojoules. I'm then going to ask, is this reaction spontaneous? By the way I've written it, it should be, right? Because I've shown by the cell potential that the more positive potential is the one being reduced. But also by delta G, I have just proven that yes, delta G is less than 0. So yes, the reaction is spontaneous. So I've proven it by math as well.